Yes, good to see you all, and thanks for that introduction, Brian. And I came here directly from graduate school to the University of Colorado. I've been here for more than 40 years, so I've never really had a real job, but I'm going to tell you about some of the things that we've been doing here, and particularly about this great adventure which recently ended in the grand finale for the Cassini space mission. So we had been involved here at CU in building experiments for missions, and I had been involved in the Pioneer Venus and the Pioneer Saturn and the Voyager and the Galileo and Mars Observer Mars 96, 98 Phobos missions, and George Lawrence and Bill McClintock and I got together an idea to design an experiment for this Cassini mission, which was forthcoming, building on our experience both with here at the university with building experiments, but also with analyzing and interpreting the data. And we had a very interesting meeting at a scientific meeting where we got together a little after dinner discussion where people suggested more people for the team. We put the team together. We wrote a proposal which was successful, and we were selected to be one of the 12 experiments on the Cassini mission, which has just recently come to an end on the 15th of September. And if you recognize all the figures here that are on the front slide, you don't have to listen to the rest of the talk, but I'm going to talk about many of the discoveries and also the end days, the final days of the Cassini mission. So we're going to talk about Saturn. Saturn is one of the giant planets. It's not quite the biggest. Jupiter is the biggest, but these four planets are similar, and we've been exploring outward from the Earth. We've had missions that entered the atmosphere of Jupiter and orbited, and we've flown by Uranus and Neptune. And Cassini was the first mission to go into orbit around Saturn. On the Voyager mission, of which some people here were involved, we flew by twice. It was a great experience to be the first, to take pictures and measurements of the planet. But then as soon as that 24 hours was over, you said, oh, we want to do this, we want to do that, or we now know a new question. And it was lucky there were two Voyagers, so there were two flybys of Saturn. But after that, after those two very short periods, we had a number of questions which could only be addressed by a longer mission. And that mission was the Cassini mission, which is extending our exploration of these gas giant planets. So the Cassini mission to Saturn launched on October 15th, 1997 to Saturn. And it took a somewhat indirect route by way of Venus, Earth, and Jupiter, and that was not for tourism, but in each of those planets we got a little gravity assist, so that sped us up and allowed us to reach Saturn in a relatively short time, only 7 years. And when we got there on July 1st, this is an artist's conception. The spacecraft has cameras, but they're pointed out, so we weren't able to take selfies. Some of the later missions have cameras that can focus back on themselves, so if you search the web, you'll find camera images of the spacecraft in space. But this is an artist's conception of our arrival at Saturn on July 1st, 2004, 7 years after launch. And that was a moment of high anxiety because we're flying as fast as we can, and at the appropriate moment the engines have to fire to slow us down so we can be captured into orbit around Saturn. And naturally, right after the engines fire, we go behind the planet and we lose contact with the spacecraft. And so, not to mention, it takes radio waves 80 minutes at the speed of light to reach the Earth. So we're all sitting in Pasadena waiting for the signal to come back from the spacecraft 80 minutes after it survived and entered into orbit to see if the mission we at that time invested almost 2 decades on, we started in '87 here at CU, to see whether we would get any of the information we built the spacecraft for. But of course, there was a great cheer. It all worked perfectly. And here's the University of Colorado experiment. It's a rectangular box. It's about the size of a piece of carry-on luggage. It can fit underneath the seat on an airplane. Of course, we don't take it that way, We first sent out the engineering model in a specially designed case built here at LASP, but it came back with a dent, and people said, we're not going to do that again. So we bought a seat for, not a first class, but just a coach seat next to the engineer to travel out on its last trip to Pasadena for integration onto the spacecraft. And there's a little challenge with that under federal acquisition regulations, but a Mr. UV experiment did have a coach seat to Los Angeles International Airport. And you can see it got the emblem of the University of Colorado here in the space-qualified radiation-protected black paint. And it's got these red covers. You probably know they've been popular for keychains and things like this. These red covers are supposed to come off before launch. If they don't, the telescopes are all behind here and you never get to see anything. So we pulled off all these red tag items. It's basically made out of aluminum, and we built it out of 3 blocks of aluminum that have been sitting on the back porch of LASP for some decades, since Mariner 9. We just hollowed them out, put them together, and that's the way to make the strongest, cheapest, most lightweight device. And so we went to Saturn, and we took this very simple tour around Saturn. This shows the orbits. This isn't the whole tour. This is just the first 4 years, the nominal tour. And why is it so complicated? Well, this was our chance to go to Saturn, and everybody on the team, of which there's several hundred scientists, wanted to see a particular view of Saturn to prove his own theory or discover his own new phenomenon. And after many years of argument, this tour was designed that covers all the places near Saturn, above the poles, and near the equator, in the back side, in the front side, over the sunset. And yes, it resembles this, which is a ball designed by a committee. Okay, well, what were we interested in? And you know, we were asked with our experiment, the ultraviolet imaging spectrograph is a set of 4 telescopes that measures light in the ultraviolet, which humans can't see. Some animals can detect things in the ultraviolet, like butterflies. But it's light that's invisible to us, and it carries information about the composition and the structure, the nature of whatever we're looking at. So we look at some things emit, like the atmosphere, like auroral glows. We saw some of those. Other things reflect light, and that tells us what they're made of. And we were asked, you know, on your investigation, what is it you want to see in the Saturn system? Because the Cassini objectives cover everything. The planet, this is just the edge of the planet here, the rings, its giant moon Titan, all the satellites, the tiny satellites, the dust and the gas, and the charged radiation belts in between. And they asked us, well, which ones of those do you want to look at? We said everything. So we looked at all of these, and I can't in just an hour tell you of all the things we discovered, but they're huge, amazing breakthroughs that are enabled by being right there, by going to the Saturn system and having an experiment we had built here, designed ourselves based on the experience of decades here at the University of Colorado. And so that curly committee design ball went past all sorts of angles, all these places, and took all sorts of views over a period of 13 years, which ended last September. So I'm going to talk briefly about, you know, what did Cassini discover, and particularly what did we find out with our own experiment, and then what are the questions that are left over. And there'll be a lot of pictures. I probably won't explain all the pictures and graphs that I show. If you have a real question, you can ask at the end. But a lot of the Cassini experience that we got was all of this information, all of these views, all these new things, the questions that we didn't even know we wanted to ask. Many were answered, and of course more questions. So we looked at the moons of Saturn, Titan, the biggest moon, bigger than Mercury, the smaller moons down to Mimas, which is just a few hundred kilometers across. And you know, if you break that to bits, that would be enough material to make all the rings around Saturn. I'll come back to that. So here's Saturn's moon Rhea, and I'm just going to point out something. There's a rayed crater like we see on the moon. That's probably a recent event. When an object like an asteroid or maybe a comet hit the moon Rhea, it excavated lots of icy material which is still bright on the surface. Here's Saturn's moon Hyperion, which looks sort of like a sponge. It's not quite certain why this is, but we got this particular view of it. It's not also quite round, and many of the things in the Saturn system have lived a difficult life over the age of the solar system. They're fragments of other larger objects, or if they're not, they're hit and broken up. So this is on the face of Hyperion. We're seeing the evidence of lots of past collisions and breakups. And here's the moon Iapetus, and it's interesting. It has one dark side and one bright side, sort of like a yin-yang symbol. And around the center, it has this sort of seam. 15 years ago they asked, well, where did that come from? And I just said, shoddy workmanship. But maybe there was a ring around the moon Iapetus, like there is around Saturn, which collapsed onto the surface. And not only is one side black and one side white, the close-up views from Cassini showed that even on the bright side, there are black spots. So I don't think you'd have to think too hard to say this looks like something that's been coated over, and then some places have been uncovered. So we think that there's been dust from one of Saturn's moons, Phoebe, that hit particularly one side of Iapetus, and then has been partly coated over by ice frosting out on the surface. Here's one of my favorite moons. Mimas looks a little bit like the Death Star. I have more Star Wars jokes ahead. So anyway, this was a very big impact. This is another example of the difficult life that's lived by objects in the Saturnian system. Not only are they hit by comets, but they're hit by other objects in orbit around Saturn. And you can see pretty much covered with craters, and the calculation shows that if it had been hit by anything that was bigger than the object that made this crater, that would have smashed Mimas to bits. And that's a pretty good thought, but then somebody said, well, of course, if it had been smashed to bits, then we wouldn't see it. So presumably, there were lots of moons around Saturn that didn't survive to be photographed by us. Okay, I want to talk a bit more about the moon Enceladus. And this was from the 11th orbit of Cassini. And the Cassini cameras find these stripes here, these bluish stripes. You're asking, why are they called tiger stripes? I don't know quite, because the idea was that some sharp-clawed animal had scratched these particular grooves in the surface, and maybe that was a giant tiger. So these are called the tiger stripes, and they turn out to be fissures, cracks in the surface of the moon Enceladus. It's about 500 kilometers across, about the same size as Colorado. And amazingly enough, we were going to investigate Enceladus, but we didn't know quite how interesting it might be. And this was one of the early surprises here. So most of us are not used to seeing magnetic fields even in yellow. But the magnetic field that is around Saturn is rotating with the planet and flies by at a high speed the moon Enceladus. And as it does, Enceladus sort of wiggles the field a little bit, but there was this huge wiggle that was completely unexpected, and it can only be the case if there was something out there above the surface of Enceladus that was dragging, slowing down the magnetic field. And it was this observation, and not the famous pictures that came almost a year later, that gave the first evidence that Enceladus was erupting, and the gas molecules that are coming out interacted with the magnetic field, and these twists and bumps were the first evidence that there was ongoing geologic volcanic activity. And one of the second pieces of information came from our experiment. So it's a little box. It's got telescopes, and you would think an obvious thing is, as I said, to use those telescopes to look at everything. We look in the ultraviolet, the far ultraviolet. But we also use a different technique where we don't look at what we're interested in. We look through it at something behind, like a star or the sun. And so you can imagine you're on your porch and you have a picket fence, and a car goes by, and the headlights blink on and off as they go by the pickets of your fence. So you would conclude something about, how big are those pickets, where they are. In the same way, we watch stars set behind Saturn and Titan, and also behind the rings. But in this case, we had planned to watch stars that would set behind the moon Enceladus. That's long before anybody said it was erupting just because we thought if there's an atmosphere around Enceladus, that will dim the light from the star and we'll be able to tell where the atmosphere is. And because we're a spectrograph, we measure the spectrum of the transmitted light. That tells us the composition of the atmosphere. And so we tried this in February 2005. And here's the star. Star gets to the edge of Enceladus, starlight goes to nothing. Such a disappointing result. That was in February. But people were talking. You know, the camera guys thought they saw a smudge on one of the photographs. You know, it wasn't very big, and they really doubt it. But it was coming from a different place. It was coming from the south pole of Enceladus. And so we said, heck, let's go see the project manager and see if we can watch another star, one that goes by the South Pole. And we went to his office, Jet Propulsion Lab in Pasadena, and we gave a pitch. It would cost not some money, but fuel. Fuel was more important than money because you can always get money here in the ground, but there's no way to get more fuel to Cassini. But he authorized using some fuel to change the orbit of Cassini so we could watch a different star that went near the south pole of Enceladus. And here's the starlight here. Starlight's coming along, but well before the star gets to Enceladus, the star starts to dim. You can see it just falls off. That's evidence there's an atmosphere around Enceladus. And as I said, we were able to measure the transmitted light, and it showed the absorption spectrum of water vapor. So not only did we find that Enceladus was erupting, we found the size of the plumes that were coming off and also their composition, more than 90% pure water. Well, at the same time, this is a great thing about Cassini, and one I'm going to regret for a long time, that NASA isn't putting as many experiments on their spacecraft. But we had a dozen experiments, so that meant while we were looking at one thing in the UV, this other experiment in the infrared, the composite infrared spectrometer, was looking at Enceladus in the infrared, and that's the temperature of warm, that's the emission that we get from warm objects. And what was expected is the pole of Enceladus would be a very cold place because there's not much sunlight there. Just the same reason the Arctic is cold. But in the infrared experiment, they saw heat. This is the same way snakes hunt. Also, you know, they saw heat coming out of the bottom of Enceladus where the sun doesn't shine. Quite a problem. And in fact, the cameras got involved in this, and you can see that they're actually seeing jets of gas coming off in this time-lapse photograph. Here's another. And the little shots of gas, like from a geyser. And where are they coming from? Well, it turns out they're coming from those cracks. Those tiger stripes are the locations. Those cracks in the surface of Enceladus are where water is escaping. And now we know that water is also carrying little bits of salt and bits of silica, so that somewhere underneath the surface where we can't get to or take photographs of, there's some nice warm water and rock and a pH that might be something suitable for life. Here's another view. Geysers on Enceladus. Cassini image shows a number of water geysers on the small moon Enceladus. Salty water from a subsurface source escaping through the cracks. You can see the curved lines of the geysers along the four tiger stripes on the surface. So those tiger stripes turned out to be the source of all the action, and they're cracks leading into some sort of environment underneath the surface where life could exist. And so naturally, we changed our plans. This is what you can do on an orbiter mission. There are many more orbits. There were 289 orbits of Saturn on the mission. So we said, let's go back on a future orbit and go right to where the geysers are, right to where the tiger stripes are, and take close-up photographs. And this is the sort of rugged terrain. It'll be something like Utah here in our country, and the cracks in the ground have stuff coming out of them. And even more, this is a distant photograph. Saturn's off to the right, but here's Enceladus again. It's a little black dot, just so tiny. It's much smaller than the Earth or the Moon. And you can see off the south, there's some plume of gas that's being emitted from the geysers on the surface. And not only that, the stuff that comes off of Enceladus, like in the space station, if they throw their orange peels on the side, they go around, orbit the Earth the same way. What's coming off of Enceladus makes a big ring around the planet, and that's actually something that was discovered in 1967. The E-ring of Enceladus, E-ring of Saturn comes from Enceladus. The letters of the rings were just alphabetical, so it's just a trick of luck that E for Enceladus gives the source for this ring. Okay, what about other moons of Saturn? Titan is Saturn's giant moon. It's got a diameter of 5150 kilometers. That means it's bigger than the planet Mercury, but it's a satellite of Saturn. And this photograph is from Voyager. It was a little disappointing because it's completely covered with an atmosphere made of nitrogen that's opaque. We couldn't see anything on the surface, but that's an advantage of Cassini. It was designed to have different pass bands to look through the clouds and also to make detailed measurements, including with radar. So Titan is about as big as the big moons of Jupiter. It's an atmosphere of 95% nitrogen, a few percent methane. Surface pressure is 1.5 Earth atmospheres. So something like what we have on the Earth. And in fact, the dominant constituent of the Earth's atmosphere is also nitrogen. It turns out that the surface temperature is 94 degrees Kelvin, 94 degrees absolute. That's about the same temperature as liquid nitrogen. So it would be hard to imagine life like ours existing on Titan, but there are a lot of biochemicals that might be used by a more differently evolved organism. Is there water? Well, the water is inside, is underneath the surface. And so people had this idea, well, at the temperature here, water is frozen solid. Mr. Wizard used to do this, freeze a banana in liquid nitrogen and then shatter it. So that's the temperature at. So the water that if it were on the surface would be frozen solid like a rock. And in fact, we do see some rocks that appear to be cobbles made of ice. I'll show you in a second that were on the surface. But ice is a pretty good rock here. And if there was any liquid on the surface, they said, well, perhaps methane, natural gas, could be, it's in the atmosphere, it could condense, rain out the surface, and there might be lakes or seas even of methane. That was a hypothesis, a speculation. The atmosphere has layers of haze, and the key investigations of Titan involved landing on the surface, which was part of the Cassini mission. It was a joint mission between the US, NASA, and Europe, the European Space Agency, and they built a probe to land on the surface of Titan. Here it is, covered with gold foil on the side of the Cassini orbiter. And you can see how big this is. It's the size of a small bus. This is a normal human in Building 170 at JPL. And the probe, the Huygens probe, is about so big. And it was dropped off. We gave the Europeans a ride to Titan and dropped it off, and it landed on the surface of Titan, just like this. So it enters the atmosphere, has an aeroshell like the Apollo spacecraft that heats up and frictionally slows the spacecraft down. The lander comes down, it's on a parachute, separates from the parachute, and falls to the surface and lands. And they checked this out also in landing in Sweden from an Earth balloon. It lands on the surface, and the surface is relatively soft. It's made up of ice and ices of water and methane and nitrogen. And it lands here, and here was the thought we might land on a very nice shoreline next to a lake of liquid methane. And that didn't quite happen, but something very interesting did happen. As we're descending, we're taking photographs, and the lander is spinning. The lander is called Huygens, after Christian Huygens, the discoverer of Titan. And you can see that the clever engineers at the European Space Agency have put these successive frames together, which are rectangular. And what they show are streams, it turns out, of methane that flow into a methane sea. Of course, it was all dry when we got there. It only rains maybe once every 1,000 years. And And as Toby Owen told me once, the rain on Titan is predominantly methane. But every millennium or so it rains and the water runs down the hills and into this lake. So it is really beachfront property, but it was dry when we landed there about here. And we have pictures of the surface. This was the most amazing thing. I was at Darmstadt in Germany, where the European Space Agency was controlling the descent, and this picture appeared on the screen. Everybody left their drinks and their dessert and went up to the monitors, looked at this. These are cobblestones. They're about a foot across. They're 30 centimeters, they were telling us in Darmstadt. And they're probably chunks of ice, hard as rock. And this one seems to be broken. There's a thought that maybe that was hit by the lander. And we measured the characteristics of the surface. It's a little bit crusty. And some of the locals said it's sort of like creme brulee. You know, it has a custard underneath and a little crust on the top. And we broke through that. And when we did that, the warmth of the lander, of course, it's really cold from our point of view, but it's a lot warmer than the surface, melted some, and the methane was outgassed from the surface. So you could imagine if you had a hot car and landed in Antarctica, you'd have vapor that would be coming up from the thawing, evaporating ice. So apparently the underside is a little bit crusty and maybe slushy methane ice. Well, we did actually find lakes, and lakes that are as big as the Great Lakes. Here's Ligeia Mare. Mare is from the Latin for sea. And Titan, similar to the size of Lake Superior on the Earth. And these were found with radar. And how do you find a lake with radar? Well, if you shoot your radar beam down at the surface, it's a rough surface and radio waves bounce back at you. But if it's flat, like the surface of the ocean, the electromagnetic radiation in your radar strikes the surface and goes off in the other direction, so it looks dark. So these dark spots were concluded to be lakes. That we had more evidence on that, but you can see right away they look like lakes. They have inlets, they have islands, they have bays, and if you've seen Lake Powell, if you've been around in there, you see where the water has risen up and filled in all the cracks in the surface, and leaving this very fractured shoreline. So they looked immediately like lakes of liquid methane, which of course is liquid above 91 degrees Kelvin absolute. Here's another view of Ligeia Mons. This is from later in the mission. Here you can see the islands and the fractured shoreline here. And this is very interesting. This bay looks not quite as dark. That's because the radar is going through the liquid methane, and bouncing off the surface. So we're seeing the reflection of the bottom of the lake here, and people can then tell how deep the lake is because they can measure the time for that signal to return, and also the absorption coefficient of the lake, which tells its composition. Mostly methane, a little bit of ethane and nitrogen. And here are the clouds. We had a challenging time looking for clouds because, as I said, it only rains maybe once a millennium on Titan. But near the end of the mission, seasonally, some of these clouds came, and maybe some of them rained methane rain onto the surface of Titan, which would then cut some of those lakes and fill in some of those bays that we saw that were dry when we landed in 2005. Okay, well, more satellites. Here's Prometheus, and you can see that it's pretty cut up. It's not round. It's got pieces broken off, and it's got lots of craters on it. So this says in the Saturn system there are lots of collisions going on. Aha! This is the moon Pan, which was named after the Greek god of shepherds, was discovered during the Voyager days. Of course, it was just a speck of light. Nobody thought it would have this skirt around it. And you might think about, well, how can an object get a skirt like that? It can if it's in a very particular location where the gravity of the object is comparable to the gravitational tides from the planet. And this is a place called the Roche limit, or the Roche zone, because it's not actually a limit. But Pan is just about dense enough to hold itself together, and if something lands on the equator, it can stick there, where if it lands on the pole, the gravity from Saturn tends to pull it off. Another possibility is they're Italian ravioli makers in the Saturn system. Okay, here's moon Phoebe. It's a retrograde captured moon. That means it's going backwards, and that it's going the opposite direction of most of the satellites. And you know, we thought about naming our daughter after a moon of Saturn, but you wouldn't want to pick Phoebe because that's the one that's going in the wrong direction, retrograde all the time. Here's the moon Daphnis that's in one of the gaps in the outer part of Saturn's rings. Here again, non-circular moon, maybe some evidence of a skirt around it, and it's definitely gravitationally interacting with the rings of Saturn, including this little wispy thing right here. So you might ask, well, we have all these broken up moons, and we have rings, how do they interact? This was one of the questions, and the answers from Cassini is they interact in myriad ways, some of which were unexpected. So remember what we knew about Saturn from those two flybys of Voyager in 1980 and 81. We had these pictures, we knew the rings here, but we didn't know the structures. We didn't have the resolution, the camera to pick out these sorts of details from Saturn's flyby from Voyager. But it is the second largest planet. It's about 10 times as large as the Earth. It's a gas giant. It's made up of hydrogen and helium. The clouds in it are probably ammonium. There's no real solid surface, and the rings are made up of water ice. More about all that in the future. So I want to say some things about the planet Saturn, which our investigation here, the ultraviolet imaging spectrograph, UVIS, was particularly interested in. And so here's Titan in front of Saturn, and you can see some interesting things here. So you can see the rings of Saturn here. They're just about seen edge on. That means that the spacecraft took this photograph just when it was flying through the equatorial plane of Saturn and with Titan between it and Saturn. So Titan's orbiting at 20 Saturnian radii, so way out here in the equatorial plane. But what are these things? These are the shadows of the rings, which you're just seeing the edge of here. Just seeing the edge. The rings are about the same thickness as this room, but from one end to the other they'd stretch to the moon. But when the sunlight, which is not in the plane, shines on them, we see the shadows of all the rings, and you can see the gaps in the rings. This is the Encke gap here, is bright. There's a shadow of the outer A ring. Here's the Cassini division, etc. And this is the thin crepe ring here, the C ring. The D ring doesn't cast a shadow that you can see in this picture. We also saw a huge storm that occurred on Saturn that puts hurricane to shame. Remember, the Earth is about so big. So the storm that we saw on Saturn rose suddenly, lasted for about a year, really messed up the clouds and did a lot of vertical and horizontal mixing. But we saw an immense Saturn storm, and this was after the nominal mission. The mission was only supposed to last for 4 years, but we kept extending it. So it lasted eventually 13 years at Saturn. Say a little bit more about this. Here's one of the structures in the polar regions of Saturn. It's called the polar hexagon, a 6-sided figure. Here's another picture. This one, you can see this photograph shows a little bit darker inside that hexagon. This related to a thesis one of our students, Wayne Pryor, wrote back about 30 years ago, and about how charged particles from the Van Allen belts of Saturn can hit the atmosphere of Saturn and color the clouds, darken them up. And we're actually, in the very last moments of Cassini, we found evidence that this is actually occurring. So here's a close-up of the North Polar Vortex. It looks like the eye of a hurricane. Okay, well, what can you see in the ultraviolet? We can see the aurora. And these are all images made by UVIS, our experiment in orbit, of the glow in the polar regions of Saturn. Here's the South Pole structure. Also the North Pole is glowing a little bit. These are the closest images we have ever gotten of the northern lights on Saturn. And because the experiment has because the spacecraft has multiple experiments, we can correlate some of those measurements with measurements of the radiation belts, the Van Allen belts of Saturn. And this was probably our best photograph, because at the end of the mission, as I'm going to describe, we were able to take chances that would not have been allowed earlier in the mission. Because the mission was ending, we could go to unsafe places to look at Saturn, and one of the unsafe places is in between Saturn and its rings. We dove through there 22 times, every time gritting our teeth, but that got us a lot closer to the planet. And on the very last orbit, UVIS made this picture. Because we're an imaging spectrograph, we can take the spectrum and also turn it into an image. Here's the North Pole of Saturn right here, and these are auroral emissions. If you'd been in there in a balloon on Saturn, you would have said, the sky is glowing hydrogen molecules. And the most amazing thing is some of this glow is coming right from near the pole, usually also on the Earth. The aurora comes from an oval that's around the pole, not on it. And this shows that somewhere in the magnetic field lines are crossing or reconnecting, and electrons they're usually trapped, like in the Earth's Van Allen belts, rain out into the atmosphere and cause it to glow. That's the glow we saw, and we could see it close up because we're taking dangerous maneuvers with the spacecraft, which we all survived. What we didn't survive was the planned entry into the atmosphere, and I'm going to say a little bit more about that later. But we made these pictures of the polar regions. You can see that's this dark area, which is probably caused, as Wayne said in his thesis, by electrons that chemically alter the cloud aerosols there. And this, you can maybe see, it looks hexagonal, so it looks like the same thing that's seen in the pictures. We see it in the ultraviolet, where electrons in the magnetic field, trapped in the magnetic field in the radiation belt of Saturn, are making visible impacts on the surface. And this was our final auroral image, and the top is the one that you would see for, if you're a scientist, you would want to know what's the latitude and longitude of all those places. So Wayne has put this on the bottom here, but you can see there is an oval of auroral emission like we see on the Earth and was expected, but there are also spots in it, and those spots don't rotate at the same rate the planet is rotating, not completely explained. They under-rotate, and there are also spots and curlicues, spirals, that go in to the polar region. And this was the last image of Saturn 2 days before the mission ended on the 13th of September. And you can see the planet's shadow on the rings of Saturn, A, B, C, D, you can't see. E is out here, and F is there. You could maybe see that if you're in the front row. Okay, well, being there is the key thing. And one of the ways that we were there is we could be in the shadow of Saturn. We could be in eclipse. And many people saw the eclipse. So there was an eclipse, several eclipses on Cassini where the planet got in the way of the sun. And that's good for several reasons. The first is you don't want your cameras to look at the sun or your ultraviolet imaging spectrograph either. So you can't look near the sun even within 15 degrees for our experiment, 20 degrees for the camera. But if the sun is behind the planet, then you can look very close to the direction to the sun, and at that point, things that are made of very small particles, like the dust on your windshield, I'm sure you've had this problem, you drive into the sun, your windshield is suddenly lit up. So the same sort of thing, these rings around Saturn lit up. There's the G ring and the E ring lit up, and also the F ring, during the time that we were in the shadow in the eclipse of Saturn. And also, there was a range, the project arranged, well, you know, we can also see the Earth there. You can see the Earth and there's another view that I saw in a political cartoon. The moon is also seen here. And, you know, NASA put out a release said Earth, moon with little arrows. And the one that I saw in the paper said White House, Congress. And the Earth from that distance is just a little blue dot. There's this famous book by Carl Sagan about this, how small and precious is the Earth. And the project arranged, since we knew this was going to happen and we were going to take a picture, well, that would be a certain time, like 3:30 in the afternoon, everybody go out and wave. So you may recognize some of these people. There's the Cassini UVIS project assistant, Laura Bloom, and several of her friends who are waving at the moment their photograph is being taken from Saturn orbit. Of course, we don't have the resolution to actually see them in the picture. So these are the rings of Saturn, and you could ask why they have these names, and the answer is they were named alphabetically with the letters of the Roman alphabet in the order of discovery. If you go to the Uranian rings, they were named after letters in the Greek alphabet, except for another group which named them numbers. So this is, other planets are more confusing. But the A, B, and C ring were found first, and then later the D and the E and the F ring. The F ring is one I discovered myself on Pioneer 11. And you can ask, well, how can I remember this? And I have given in my general astronomy class students the assignment of making up mnemonics to remember the rings. So Esposito, great for astronomy, but can't draw. It's something about my blackboard skills. Okay, so here's how it would really look. This is a natural light mosaic of Saturn and its rings. And this is how it would really look if you were on Cassini. So lots of times in the computer we do enhanced color, or sometimes with UV light there's no color. So it's purely artificial. We get to pick the colors though, so I'll show you some of those later. The captions for these are directly from the project. So if you go Google stunning views on Cassini, you'll be led to this particular photograph. Here once again, this is easier to see. Here's Saturn's rings and the shadow of the rings. So each one of these little narrow rings casts a little shadow. Here in the C ring, those are the C ring plateaus. And then the B ring and the A ring here. Aha. So this is in the infrared. How does Saturn look in the infrared? And once again, this is with visual and infrared mapping spectrometer. They got to pick their colors. And that's how Saturn and its rings would look if you were a pit viper, a snake. Here's the butterfly's eye view of Saturn's rings in UV. This is what we made with our Colorado experiment, where we take ultraviolet light that was reflected by the rings and turn it into a color, an artificial color. And so the red, I have to tell you, that is basically the emission of neutral hydrogen. The whole universe is full of hydrogen atoms. And wherever the rings are thin, or this is the Cassini division, there's a gap between the rings. That light from the whole universe, hydrogen, Lyman alpha, shines through, some through the C ring. But we can also see the bluish color, the bluer it is, and that's why we pick these colors, show more icy rings. And the rings are more icy as you go out. I don't have an explanation. So what do the rings really look like if you were there? And this is an artist's conception. We hired this fellow, was a colleague of Laura Bloom's, my assistant, and he was an artist, and we gave him some of the data to look at what might look like if you're in the ring. So chunks of ice that are clumping up. They clump up. And these clumps, the clumpiness of the rings going on the way to becoming moons, or maybe shattered to make rings again. We got more and more of this information as the mission went on. Okay, well, I showed you a similar picture to this before. Here's the moon Enceladus. Here's the plume. Here's the shadow of Enceladus on the E-ring of Saturn. So we can see a ring being made right in front of our eyes. So that's not quite the same thing as these big rings. It's very much more diffuse. You have to wait until eclipse to really see it. The small particles also make up rings. Here's the F ring again, which seems to be in between two of the moons of Saturn. One we've seen before, Prometheus. I showed you a picture of that, and Pandora. And the ring resides in between these two moons. And the idea is they operate something like sheepdogs, gravitationally like shepherds, and keep the ring in place. I'm not sure that idea is right, but it at least explains what we're seeing here. And of course, the moons are near the rings. They interact through their gravity. And additionally, I don't know if we have any people, we've done a number of PhD theses here at the University of Colorado about spokes on the rings, these sort of lanes here. Can you see that? So these, if Saturn's rings are round like a bicycle, and these things have structures that are radial, that point directly outward like the spokes on a bicycle wheel. Some of the more amazing things, there are waves in the rings, and these are important for the history of the rings. And here we have waves propagating through the rings, one in this direction, one in that direction. This is that little moon Daphnis again, casting a shadow, but at the same time it's stirring up stuff around it. And the situation is that Daphnis is going slower than these particles in the rings, but faster than those, so the perturbations are on the left above and on the right below. Here's the C ring from August of 2017, one of the last images. Here's the rings from beneath on the 9th of September. There was less than a week left in the mission. We're still, you know, like a test pilot who's ordering in. We're still taking photographs all the way down to the end. A quintet of moons around Saturn. Saturn has 63 known moons. Here are Titan, Enceladus, and Mimas. Here's the rings from below. The rings from the side, you can see the shadow again. So once again, this is the Cassini, the Yankee gap here, and there's the shadow of the bright spot where the light shines through the gap. Here's the C ring from August 2017. And while we were flying inside the rings, we slewed the spacecraft around to take these pictures of the rings. So this is, you can see a mosaic again, one picture after another, as we zoomed through the ring plane and underneath it to take this view, which obviously nobody has ever had before, which was too dangerous to take unless we were heading on the way to the last roundup, as we were. And this was the very final ringscape, and you can see here's the F ring out here. It's somewhat inhomogeneous. You can see the Cassini division, it's not empty. You can see the D ring has some small strands in it. That's the last rings from 9 September 2017. And I wanted to say a little bit about Saturn's F ring. This is a stellar occultation where we watch a star set behind the ring, and we see how much opacity there is, how opaque it is to light. And we see the F ring. This is going to be one. This thing right here. So the star passes behind the F ring, and we see that. But then there's suddenly the star basically blinks out. And I had the idea that these must be transient structures in the rings that come and go. And so therefore they have like 9 lives. And I started naming them after cats, including our own pets and some that memorialized that had passed away. And it was picked up by the reporters after the flyby. So these are the kittens in the rings, and particularly this was a cat that the reporter wanted immortalized in her article. And my daughter sent me this on Facebook. Her name is Rhea, so we did name her after a moon of Saturn, but not Phoebe. Kittens orbiting Saturn, cosmic kittens. Saturn features get feline names, and we still have some, but we haven't named yet, so I'm still collecting names of cats for these. And we distinguish on how much light they block. And so you see these are 3 different cats. Some kittens block more starlight, so they vary in opacity. And I want to say something about these structures as well. This was actually predicted before we got to Saturn, that if you had a little object in the ring, and I showed you Daphnis, which is in the blank space in the rings, and Pan also, they're in a gap in the rings. But if an object is small enough, it only makes a partial gap, and the computer calculations show that that would look like an old-fashioned propeller. This was just a hypothesis, but now on the mission, especially at the end of the mission, we got close. We got to see all these little propeller-shaped features. So they're just slightly offset. They look like a couple of dashes, but there's one up and one down in each of these cases. Here's the largest propeller So I had started naming these structures in the F ring after cats, so Matt Tiscarino started naming these propellers after famous aviators like Wright, and this one's Blériot. And here are a bunch more. See this one right here? See, that really does look like a propeller. So many, thousands and thousands. In addition, clumps and strands in the rings. I've shown you the shadows of Saturn's rings here on the planet, and the shadow of the planet on the rings. There's the dark side of the rings. You know, it's nothing evil, but the sun is on the other side. You can see through it. That makes useful investigations. And Saturn has a seasonal appearance where, as it goes through its season, at the equinox, we're looking directly through the line of the rings, and they disappear. In fact, even from Earth, Hubble can't see the rings at the moment that the Earth passes through them. And this, with the mission being extended to 2009, after its original 4-year design, and before the 13 years it actually survived, we realized we were going to come up on equinox. And then the rings disappear. So you can just barely see them here. There's another view, rings disappearing. But that wasn't the key part. This is sort of like occultations. You don't look exactly at what you're interested in. Well, you know, during the time when equinox occurred, the moons would cast shadows. So here's the moon moon Mimas casting a long shadow on Saturn, its rings. And I don't know if you've seen this picture before. It seems to be a picture of camels, but it's not. Actually, these are the camels. They're lit on one side, dark on the other side, just taken at sunset. And these are the shadows of the camels taken from an airplane. This is another indirect technique. See if you can make the connection here. Look at all these triangular shadows. This one comes from right here. So what we're seeing here are the shadows of structures that are sticking up out of the rings. Der Gipfel des Berges funkelt in Abendsonnenschein. So the tips of the mountains are sparkling in the evening sunshine. That's from Heinrich Heine, the Lorelei. And we were able to detect, just like this, you could never see the camels except for their shadows. We were able to detect structures in the rings. Completely unexpected that. In addition, little elongated structures in here, in between those density waves. More straw. So take a look right here. Look at this stuff. Nobody has an explanation for this. I'm working on an explanation. And here we have some regular structure. This is overstability in the rings, and also this straw-like feature. So we're seeing structures in the rings that could never have been seen before because it's so small. Here's the outer edge of the A-ring. See all this straw-like structure is something unexpected and difficult to explain. But luckily, we have data, and undergraduates here at the University of Colorado look at our occultation data, watch stars go behind the rings, and she's pointing to one little feature in here. We decided to plot out one of our occultations and just put it along the wall. It's 100 feet or so. And each one of these little features is something in the rings, a real structure. Luckily, we only have 173 of these occultations, so we couldn't put them up on the wall, but we have been analyzing them, looking for waves in the rings. And this is a wave in the rings. That one right there, it's a density wave. Karen, you probably recognize this structure like what we saw in Voyager, but there's something extra. There's an extra thing in there, and by taking multiple occultations, we could see this thing move through. It's a solitary wave, a soliton moving through the rings. And we're able to measure scales that are on the size of this room now with our occultations, where the rings are completely transparent. There are gaps in the rings. So this is even beyond, 100 times beyond the resolution of those pictures I showed you, as finer and finer structure. And here's the moon Daphnis making these edge wakes, which then form clumps and actually gaps. So I'm thinking these sorts of gaps, which are big enough to be seen by the cameras, are what we're actually seeing in our occultation data. Do I have any explanation for this? Yes. Not a really good one. It's an ecological analogy. Involves foxes and rabbits. But the idea is that things oscillate out of phase. And this simplified model allows us to explain some of the structure in the rings. And I can't say too much about that, but I do want to say that one of our former students here, Robin Knupp, has an idea for how the rings formed, which was a moon that got too close to Saturn and was torn to bits. Unfortunately, the very latest data from the grand finale doesn't support this model, so we're out without a good model at the moment. I wanted to mention, one of the great things about Cassini were all the people on it, and here's a picture of some of the women on Cassini, including the chief scientist, the project scientist, Linda Spilker, and the spacecraft chief, and the operations chief, and etc. So a lot of the chiefs, not just the Indians, were females on this mission. Okay, well, it's almost the end of my talk, but I want to say about Cassini's grand finale, how did the mission end? Once again, an artist's conception. And what were our objectives? Main one was not to contaminate the moons of Saturn, which might harbor life. We didn't want to smash Cassini spacecraft full of germs from the Earth on that. In fact, there's a treaty that says we can't do that. And so we have to dispose of the spacecraft by burning it up in the atmosphere. There's unique science we're going to do, measuring the magnetic field and gravity. We get so close. Measuring the ring mass. I'm going to say a little bit about that later. And also in situ measurements of the ionosphere and radiation belts. And we backed some of us up with spectra that we took at the same time. So the final months were spent looking at Saturn and its rings from these orbits first grazing the rings and then going inside. These blue orbits all go between the ring and the satellite, the disk of Saturn. Those are the final grazing orbits, and then the proximal orbits, the grand finale orbits. So we're really in close to Saturn. The orbits just lasted a week, which was a real challenge for everybody operating the spacecraft and people trying to analyze the data, especially for safety, since we'd never been there before. And eventually, those last orbits end up where the last little blue line intersects the planet. That's the end of the mission. And so I want to show you the final hour of the mission. And we zoomed in. This is 1 hour. We zoomed in and hit the surface, taking photographs all the time, the best photographs ever taken of Saturn. And in the last 90 seconds, we zoomed in, hit the atmosphere, and like a meteor, the spacecraft, which is never designed to do that, began to tumble, burn up, melted, and vaporized. And we made measurements here with our experiment. We were on to the last minute, had data to the last transmission. We measured molecular hydrogen and nitrogen in the atmosphere. The hydrogen is probably part of Jupiter's atmosphere. The nitrogen is probably coming from the thrusters, which are trying their damnedest to keep the spacecraft aligned, but eventually failed. And so here's one of those last pictures. This is the closest ever color view of Saturn. So what's my summary? So the Cassini mission, which originally was to last 4 years in orbit, lasted 13 years and then crashed into Saturn. The Huygens probe landed on Titan in January 2005. Spectacular pictures and measurements that tell us about that world, which is in many ways like the Earth. Cassini observations of Saturn's rings showed them to be highly active, changing before our eyes. Just amazing stuff. And the mass of Saturn's rings is now known to be about half of the mass of the moon Mimas. And Cassini dust measurements, another experiment that's directed here at the University of Colorado, measured the impacting flux onto those rings. And because the impacting flux is sort of dirty, it pollutes the rings, but they're very bright, very pristine, so that means they can't be very old. So the Cassini data, the measurements of the mass and the dust, say that the rings are very much younger than the solar system. We don't have an explanation for that. Titan has ethane, methane lakes and rivers. Some were wet, some were dry, some were slushy, like where we landed. And Enceladus has a salty ocean, including tiny quartz grains, probably from hydrothermal vents, like the vents underneath the oceans where we find biological communities on the Earth, with some organic material and it's spraying it into space, making the E-ring. I showed you the photographs of that. And both these last two places in red, Titan and Enceladus, are both great places to go to look for life, different types of life. So that was the end of the mission. Many of us were there at the Jet Propulsion Laboratory. Others were here at LASP watching on the TV, the transmissions, and the mission ended. A mission that I've been working on since 1987, since we wrote our first proposal. We got selected for flight in 1990. We delivered our experiment in 1996. It was launched in 1997. We operated it past Venus, an asteroid, Jupiter, into orbit around Saturn, and through 13 years of extended mission, not only interpreting the data and writing papers as we could, but changing up the operations, improving our ability to use the spacecraft and follow up on questions. And it was a sad day when that all ended. It was a sad day, but the good news is that Cassini leaves a wonderful legacy of data for generations of scientists to work on. So I thank you for your attention. I'd be glad to take some questions if anybody has a question. Yes?
How do you guard against contamination of Titan from the Huygens probe? Yeah.
So the Huygens probe was heated, but that was a job that the European Space Agency took on, and I don't know the details of the sterilization and the heating process. There are protocols here in the U.S. that we used for the Viking missions to Mars, and I understand they use similar techniques, but I don't know exactly what they were.
So basically they heat it.
Right, and for the Mariner and Viking spacecraft, there was a hydrogen peroxide wash as well. So dry heat, baking, and a wash with a sterilizing agent. Yes?
You said there were 13 or 12 instruments on Cassini?
Yes, it's true.
All survive until the end?
Not quite. One of them didn't, and the lead on that was Frank Query, who was a student here. He was one of the last leaders of that mission, which had a failed power supply, but many years after the nominal lifetime of 4 years. So, and on the radio science investigation, they had an amplifier fail. For the most part, all of the experiments, with those two exceptions, lasted to the end, and even the ones that didn't last to the end, they lasted well beyond the 4-year lifetime that was planned for the mission. Sir?
On the pictures of Saturn itself, the edge looks so well defined, and whereas the pictures edge on the Earth's atmosphere, you get this fuzz as it fades out. Is it just that they're too far away to see the fuzz, or is the surface that well defined?
None of these images has been artificially sharpened, and it just depends on the real perspective that you have. So there are some perspectives of Saturn where you can see the scale of the atmosphere declining. But the ones I showed you are from a distance, and at that distance, the scale height of the atmosphere is about 60 kilometers, and we're typically about 60,000 kilometers away, so the cameras just can barely resolve that fall off. But if you go to the Cassini website, you can see more diffuse pictures of the Saturn atmosphere. Sir?
I was amazed you could keep taking pictures so close to the end.
So they're actually not right at the end. They had to stop a few hours ahead. And not because of the shuttering, but because because of the data, the data rate, the data mode we were in, it couldn't accommodate taking those big pictures because you have to store them, and then they wouldn't come back. Alan, do I have that right?
Yeah. And then transmit them back to Earth.
Right, so all this transmission was done in real time, so that's why there were no pictures at the very end. Whereas our spectra we could take in a second. So every 48 seconds we got and so the last spectrum, I didn't show it to you, but the last spectrum we shows the emission features of molecular hydrogen and molecular nitrogen. We see that in the last seconds before the spacecraft antenna turns off the Earth, and then it's within a minute that it burns up. Anybody else? If not, thanks very much.